We often need to make decisions based on observations. When we can make these decisions with desired confidence is an important problem. As a simple example, we may want to decide if a coin is fair. We keep throwing the coin until at some point there is enough evidence to conclude that the coin is biased. Such a problem can be modeled as a random walk by counting the number of heads minus the number of tails. We keep throwing until this value reaches unreasonable thresholds and make confident conclusions. By studying the properties of random walks and how unlikely large deviations happen from what is normal, we can find efficient strategies for this problem and many other problems. A typical inequality takes this form. We find a boundary the random walk crosses with probability no greater than delta. A common choice is the Hoeffding bound. However, this bound only applies to a fixed time n, but it fails when n is itself a random variable. This makes it significantly less useful, as most algorithms make decisions not at a fixed time, but in random time, dependent on the actual samples observed. We need a bound that is adaptive to any evaluation time to be applicable to these problems. In fact, for a bound to hold for any time n, it is both necessary and sufficient for the random walk to never cross the bound for all time n up to infinity. For any bound that scales asymptotically as square root of n, it can be shown that threshold crossing is almost sure to occur sooner or later, even though it is unlikely to occur at any fixed moment. It is a known fact that boundaries scaling asymptotically as n log n is both necessary and sufficient to bound the probability of ever crossing. As our contribution, we provide the tightest bounds known to date and achieve state-of-the-art empirical performance on a variety of problems while retaining good theoretical guarantee. In particular, we show that this bound has controllable crossing probability and is significantly tighter than bounds in previous works. We also analyze batch sampling schemes where we sample a batch of samples at each time step, which leads to better constants. We show that our algorithm significantly outperforms state-of-the-art alternatives on hypothesis testing to see if a random variable has positive mean, and best arm identification. For detailed information about the implementation and baselines compared, please refer to our paper.